Okay.
Hi, Pat.
Hi, Sophia. How you doing?
Pretty well. How are you?
Okay. Okay. I'm getting ready to go on a trip, just a brief one,
Ooh, where you headed?
just to Palm Springs.
Very nice.
Yeah, it's,
I'm at Universal Studios right now, actually.
you're where?
I'm at Universal Studios.
Where in LA?
No, in Florida.
Oh, in Florida.
It's about a 3-hour drive from my house. My mom and I decided to go uh, and just take a few days to go come up here. So we're up in Orlando right now.
Nice. So it's just a little party time, huh?
Yeah, it's a little fun.
Yeah. Yeah. I've never been to one of the Universal Studios things.
It's been really fun. It's been kind of surprising because I went to Disney Springs with a friend of mine like last year around this time. Everybody's actually wearing their masks. And like Universal's actually enforcing it even in the ride, like in the lines for stuff and indoors and all of the things. People are wearing masks over their nose and mouth, and it's very, very nice to see, even though we're in Florida.
It's amazing. Yeah, you don't see that. You don't see that often. Not in Florida, but yeah, nobody. It's funny how it's very regional. I was looking at people getting ready for the Super Bowl in LA on the news, and everybody in LA was wearing a mask. I think they're going to be required to at the Super Bowl too, which I'll see. That'd be amazing to see. Trying to get everybody logged in here. We've got a good group. Okay. So, okay. We got Russ, we got Dave. Dave, what part of the world are you in now?
I'm in Colombia.
Yeah, okay, okay.
You can tell from his background.
Yeah.
Yeah, I was just goofing around with backgrounds.
Yeah, yeah, they're fun. But how much longer are you going to be there?
Until the middle of March,
Oh, okay,
about the 14th, I
okay,
think.
okay. What is the situation as far as the Mount Wilson engineering
Well, as far as we know, it's going on.
going
LA.
on? I got
March 25th. Sorry, you caught me right as I was eating a
I
chip.
never thought I'd get you speechless, but that's good.
March, wait, is 25th a Friday? So it's not Friday, Saturday,
Okay.
which is.
Yeah, that's what was originally planned, yeah.
Mhm. Yeah, that's still the plan. I'm hoping to do some Milaning too that weekend. But do you guys want to go up on, is Rick here? Rick's gone. Rick, come back.
There he is.
Rick, do you want to go up on the Friday or the Saturday or both?
I don't care, either one or both. I guess we'll stay overnight.
Yeah.
Right.
I'm gonna get in on Thursday and stay with Dave that night. Thank you, Dave.
You're welcome.
And I
What
will.
are the dates again?
March 25th. I'm looking at
Okay,
the
thank
February calendar, but yeah, so it would be, so I'm gonna get in on the 24th in the evening, and then we could head up the 25th, and like Tom was vague about which of those 2 days, maybe both. We could head up on the 24th, and I just finished composing a delayed send email to myself for Sunday to all of you actually, that on at the Instar meeting last time, we had said we were going to have a like target selection protocol discussion. I made up an acronym for it, even GTSP, General Target Selection Protocol. And that would be, because Reed made the point last time, which is a really good point, that we should have targets selected in advance along with reference stars and multiple catalog names and a bunch of other things before we go up, and then we can cycle through them without doing any kind of messing around trying to figure that stuff out at the telescope. So we were thinking to iron that out at the coming Instar meeting. Just like as much, generalizing it as much as possible. Russ, who's also not here, Russ has a vision of just having a sort of list of steps to go through that would then be applicable to any telescope, any night, any like, you know, set of parameters. So we'll figure out what parameters would play into that. But yeah, I'm excited. I think this is going to be quite a run.
Like,
Well, is the plan to?
I'm
start
here,
working
but I'm
there
just not showing.
I'm sorry. I see. Go ahead.
Russ is there in voice only.
Yeah. Is the plan to start during the day on Friday? I'm just trying, because I would like to join you on it.
We can, like I
Great.
said, I'm getting there on Thursday night, so I'm game to head up whenever people want to.
And then observe on Friday night? And
Sure.
Saturday night too, or is it
Yeah.
just Friday night?
That we've been really vague about that. but we could do that. Do you think you'll be able to come, Pat?
Yeah, I'm pretty sure planning on coming for the
Yay.
25th and overnight for the 25th. So I don't think
Okay.
I could do both. I don't think I could do the night of the 26th as well.
Okay, well, let's plan to go up on the 25th and do it then. I'll bring dinner. This time
Thank you.
for real. Rick remembers the last time I said I was gonna, or one time I said I was gonna bring dinner to the Orange County telescope and forgot, and we had to eat popcorn all night. I will bring dinner this time.
Clay, I've got a bunch of stuff going on in my life over that period of time, but I still have hopes of coming. So if you can just keep a spot open, I'm trying to plan on it, and we'll see how it turns out.
That
If
would
you want
be
me to
amazing.
drive, if you want to drive up there together, Scott, that'll save you one logistical hassle too.
That's a good idea. I like that, Pat.
Okay. That'd be fun.
Yeah.
I hope
so
to come
if-
also.
Russ, you gonna come?
I hope so, yes.
You
Yeah.
wanna stay, you wanna come Thursday night so that we can head up Friday?
Absolutely.
All right, I'll pick you both up at the airport if I can get, if you can make the times similar enough.
Yeah, I'll coordinate with Clay, and so we fly in about the same time.
Okay,
Great.
I'll shoot you an email right after this. We just need Leon and Tom. Sophia, are you gonna come? Actually, there's an OHS event that weekend as well. So I don't know if
There
that's
is?
your plans, but
Was
am I
Sophia
not
planning
supposed
to come?
to say anything?
If the 25th of March, I will, if you send me that date after this meeting, I'll check my calendar. I think that's OHS spring break, but
It
and I
is
can try and make it, but I
It's
gotta check.
it's OHS spring break, but it's also an event that I may or may not have been allowed to say anything about yet. No, I think it's public. There's like a pixel gathering thing, but whatever. You can figure that out. But
Yeah, if you
let
send me an
me-
email with the details after this, I will take a look and get my calendar straightened out and let you know.
coolio, I'll send an email around to everyone. Leon, can you come?
If you find some very cheap international flights, sure.
I know, alas, I wish. Yeah,
Leon, I might have some frequent flyer miles that I can throw at you. I don't know. If you, would you be interested in coming?
If it's a serious option, sure.
Yeah, it's a serious
But
option.
I don't know how flyer miles work.
I'm not sure. I'd have to find out exactly how I could get them to you. That would be I have to call.
Yeah, that'd be amazing. Yeah, sure.
Yeah, that would be wonderful, wouldn't it? We
That'd
have
be really
a,
cool.
we have a group meeting on Mount Wilson.
It'd be
Exactly.
a lot of fun.
That would be a lot of fun.
We'll have the Friday afternoon meeting on Mount Wilson. That would be.
Exactly.
Yeah.
Hey,
And
Grady,
I got a big pickup truck that'll hold 5 people. And so I can ferry everybody around and I got a place to stay if you want to come, Leon. Put you on the couch in the living room.
hey, Grady. Could you fly a bunch of people over?
Hey, there you go.
All right, so yeah, Friday on Mount Wilson, if we can get Tom Megahini to agree to that, Friday, and why not Saturday? We can have fun. You know, it's such a beautiful place to spend a Saturday hiking around or whatever. That would be fun.
What date is it, by the way?
It's the 25th of March,
Of March. Okay.
Friday, the 25th. I hope Calais got that right. Is it Friday, the 25th?
Yes,
Right.
yes, it is. And Tom has already said that we can stay in the monastery, which I believe is, it has plenty of space, but if you tell me for sure, if people can tell me for sure, I can give him a head count, or I can just say 10 people and we could have less.
We could also drive back down the mountain in my truck and you can all stay with me because it gets cold on the mountain. So
That is the rub.
I've got about 20 sleeping bags at Rowville, so I'll bring them all back down. You can all crash on the floor.
That sounds fun.
I get 2 beds, 3 beds, and a bunch of floor space. So
Pajama
we
party.
can have some serious fun. Hope everybody shows up. We can kind of do it Colombian style. You know, that's what they do here. Everybody shows up to a house and you just crash wherever, there's a spot.
Interesting. That's fun. That's fun. Okay, well, we should send Kalea an email if we're planning on what your plans are, so we can so you can get it booked in the monastery. Cool.
And we've also got a muon detector to build.
Yay, I'm so glad that that's like being mentioned by people. People who
And I
are
have
not, I'm so excited about that.
I have no idea whether I got all the stuff, and I'm in Colombia, so I can't check. But when I get back, I'll get the stuff ASAP. Okay.
Sweet, thank you.
Good. Good. Well, I've got one thing that relates to Bass Road. Grady particularly is working on the configurations of the stuff. We sort of come around to the feeling that I think I mentioned before, we're too happy about using an FLI filter wheel, knowing the problems you can have with equipment that can't be supported. So we figure we'd just go ahead and change out. And after kicking around with a lot of people, we've come up with the Starlight Express model, a 9-position filter wheel with round 2-inch rounds. And just want to throw it out there, if anybody's got opinion about Starlight Express. We've gotten, generally people think of, when we give them say Optec, Starlight Express, they tend to go, no, not Optec, I mean QHY, they tend to say, no, go Starlight Express as a preference. Does anyone have a strong opinion about it? No? Okay, good. And that was an uncertainty we were working with. Anything else on there, Grady, that might be useful to?
No, we're getting all the filters coordinated, the Starlight Express, the QHY 600M. PowerMate's being worked up in the quote right now. The computer you and I have settled on.
Did you settle on the PowerMate or the big Barlow? There's two different.
The PowerMate 2.
PowerMate 2.
I thought that
PowerMate
the 2X version, I thought that was the general consensus?
The big Barlow, I think, is probably our best option, given everything.
What do you mean?
All right.
Which Barlow?
It's called the Teleview Big Barlow. It's a 2X,
Yeah.
2-inch diameter.
All right, so we're off the PowerMate. Teleview Big Barlow.
Right.
They actually
Plus,
have
isn't
different
that-
optics, right, Dave?
I'm sorry, Rick?
Don't they actually have different optics? The
Well,
two,
yeah, it's just a Barlow is just, a group of 2 or 3 achromatic lenses,
right.
negative power. And I found from simulation and modeling that that's actually it's as good as the PowerMate. The PowerMate is nice because if you extend the focus backwards, you don't change the magnification very much in a telecentric system, but we really don't care. We're going to have a fixed focus distance between the Barlow and the sensor. So it really doesn't matter to us. And it turns out that the 2X Barlow will give the big Barlow, the Teleview Big Barlow will give us about 2.4x magnification if I've got the sensor position correct.
I have a question. So I'm on telescopes.net, which is who we're working with on the quote of some of the accessories. And I type in Teleview Big Barlow and it looks at me like I have 3 eyes. What do I call this thing?
Well, you go to the Teleview site, and which if you let me share my screen, I'll
Sure.
show it to you.
Sure. Yeah, I'm a little confused. I thought they were all called PowerMates, so I didn't know if there was a distinction.
Well, let's see what I can find. If I go to the Teleview site. I was just there. You.
UE. No,
Oh, it's
no,
V-
UE.
E, right.
Yeah.
There we go. Okay, so Teleview. Let's just go to the mobile site. This works. So down here, there's Barlow imaging.
Mhm.
Okay. And 2X big is the one that you want to look at. So 2X big Barlow 2-inch at 44 millimeters, 45 millimeters gives us 2.5x. Okay.
No, because
And this is the
dumbass.
this is the Teleview Big Barlow. And I've had one for 20 years. It's an excellent piece of gear.
Teleview 2X Big Barlow.
Teleview Big Barlow 2X.
Big dude on the right. All right.
2X.
I don't know this for a fact, but it's my impression that that was their original design, and then they came up with the PowerMate, a different design, and they really have marketed that and pushed it, in part because maybe there's some better some advantages for using it with eyepieces, but they also make more money on it.
Yeah, so here's the PowerMate line. And you notice that the first 3 PowerMates have a constant magnification versus distance to the sensor, right?
Uh-huh.
And then I don't know what this is. It's like not even a telecentric. They call it the 5X PowerMate. So whatever that is something odd, but unfortunately, the 2-inch, the 2X PowerMate that comes in a 2-inch has only a 2X magnification, and I would prefer more magnification. We can also try someday the 4X, drive up to SRO and stick it in if we've got enough swing through distance. And that would give us the ultimate resolution for the 17-inch CDK.
Okay. Well, I'm glad we had that discussion because I did not realize that there was a distinction. I thought they were all PowerMates. Okay.
No, I think like Rick said, the original Big Barlow goes back a long way. And then they came out with the PowerMate line
Okay,
for whatever reason.
great. Well, thanks.
I'm guessing that the big Barlow is just a simple negative lens like any other ordinary Barlow.
Yeah,
I
I think
think
it's a
the-
3-element achromat,
Yeah,
negative lens.
but the PowerMate actually has two sets of lenses that interact with each other, right?
Right. So
Almost like
yeah,
a Barlow within a Barlow.
there's a double achromat,
Huh.
2 sets of achromatic lenses in a classic telecentric configuration.
Okay,
And one of the concerns I had with the telecentric design or the PowerMate design is that the first element is fairly small. And it might be causing some vignetting right up front because it's the first thing that the optical path sees.
okay.
Yeah, you have to do a ray trace to see
Yeah,
what would happen.
I don't know what happens, but presumably the big Barlow, so-called, has a larger hunk of glass there.
Well, it covers about a 45 millimeter diameter field of view.
Yeah,
Okay,
And that's going to be as good as we can get in a 2-inch.
right. That's almost a
Barlow.
full 2-inch aperture.
yeah, yeah.
My 2.5 power Barlow, the first element is only 23 millimeters in diameter,
Wow.
which is, I don't know if it's vignetting or not, but it makes me nervous.
That's
I
for an
wish-
1.25 inches, and it's less than an inch. That's interesting.
No, it's for a 2-inch, but it's less than an inch.
Oh, my God. Oh,
Well, that's because you're intercepting the light cone close to the focal point. So,
Right,
you really can't go by that. You've got to look
Yeah.
at the,
yeah.
yeah.
I wish I had known that
Nonetheless.
the big Barlow was available because I probably would have got that, but that's what I really wanted, but I didn't even know it. The TeleView site makes it really hard to find things to me. I
Yeah,
never
it's-
even knew it existed before Dave
Right.
mentioned it in his email last week.
Right.
Yeah, yeah.
So Russ and Dan and Eric and I stacked about 4 of them together. The first time we were ever at, we did speckle at Rowville for the first time in like 2012 or 13 or something like that. And it actually worked pretty well. The optical quality was, I didn't try to model it, but the optical quality was totally acceptable. We got really quite excellent speckle. So you can stack these Barlows and you get very little spherical aberration from them.
As I recall, I took a hacksaw to one and a hose clamp to get it all together.
I couldn't watch. It was such a horrible thing. Russ with a hacksaw going after his Barlow, but yeah, that was fun, Russ.
That's funny.
In fact, Russ has a picture of it somewhere, the optical train. Do you still have that, Russ?
Yes, I do. Yeah, it's a funny one.
Okay, well, where do we go this week? Now we've solved these world's problems.
Okay, so where would anybody have issues that they'd like to talk about?
I have a general complaint. Ever since I started off-axis guiding, I've had to remodel my dome because the dome slot is no longer pointing. So both the telescope and the guide are included.
Right.
And I can just show, that's actually what I was doing right now. As the weather was good, well, better than normally. I just pulled up a nebula here with looping 10-second exposures. And I'm looking if the nebulosity increases or decreases as I change the numbers in the dome values, because the actual measurements I've made, if I enter that with this equatorial mount, then it's pointing at the wall. So I have to give it fake numbers. And now it's completely clouded up, like this is through haze. but I can definitely see the advantage of the L600 or L350 by fighting with an equatorial mount inside a dome.
Yeah, fighting with a German equatorial style is real difficult, you know. So a fork mount or any, you know, thing that looks like a fork mount where you don't do meridian flips, it's much easier to manage in every
This
way.
is not very high in the horizon currently. Here it's 32 degrees altitude.
Mhm.
So this is I'm pushing it to the extreme and seeing if the dome still follows. And it's a fight. And the other news is before Nick was feeling worse a few days ago, we did some more work here on the live view, because on his computer he has a small, it's basically a planetary or guiding camera. The company uses it as a polar alignment camera, and he's got up to, I think it was 15 frames a second, but we couldn't repeat it. So what we're doing now is, this is my observatory laptop here. We're going to install Visual Studio on here and use this QHY camera. And just bug fix it. Currently, there is progress. It used to be at 0.6 frames per second. Now we're up to 5 frames per second, which is already in the acceptable range if we're doing 100 millisecond exposures for speckle. But the images, they turn out in 0 to 2 ADU values. It's some conversion issue from live view to FITS, because I already checked the hot pixels are in the exact same position in that weird messed up image. Actually, I may be able to open it, but the difficult part is completed. That is getting live view working and saving the images, even if they're not saving correctly. So that's
what format do they save in?
They save in FITS.
Oh, they save in FITS. Oh.
Why isn't maximize there? It's weird. Yeah, these should be it. Oh, this is just completely black. Could be that I deleted them. Yeah, these are completely black. I upped the gain. These are with a low gain setting now, but all these are all 0 or 1 values here. And we used to have some small hot pixels here and there, and those match the same position. So it's some saving issue, but that should be relatively simple to resolve in comparison to getting it working. But I don't know how to do that. It's entirely up to Nick.
How did you get
He can now work with this QHY anytime he wants.
How did you get the frame rate
you
up?
and Nick are working just on the you're not working on the ZWO cameras, just the the driver for ZWO. You're just working on the QHI.
Just the QHY, but the nice thing here is, I can't show you, but here I have a ZWO and a QHY camera plugged into here. So if both are working, then we can compare.
Yeah. And do you know what the frame rate is you're getting out of the ZWO?
Sadly, no, but it should be able to be just as high as well. Because remember, he's also using a QHY camera, just it's a planetary camera, and he gets 15 frames per second there, or even more. So still some issue with the cameras.
Yeah.
And also interestingly, a larger region of interest in the same aspect ratio as the sensor had a higher frame rate than a square with a smaller region of interest. So you have some testing to do there as well. I don't know.
Yeah.
It's weird.
Software.
Huh.
Well,
Okay.
Leon, so I asked Frank Suits, he's a good friend of mine, and he's the one that wrote a tool called SpeckleCap a while ago for me, actually now many years. And he got quite interested in the problem. So he has a QHY 500 something. I don't know. I think it's a guider camera. And he said he'd take a look at that for me to see what the state of the QHY, drivers is, what are, I don't know. And so he took a look and he said that he could make speckle cap work with the QHY, with his QHY 500 something or other. And he thought it would be worth a try to try it with the QHY 600, with everything, region of interest, camera cooling, the whole thing. So we might have a backup plan there if you can't get satisfactory results from QHY, from the drivers, from the whatever you're using, the software development kit or whatever.
Yeah, sure, that'd be great. But well, I'd be very interested to see the difference between the guider camera and the 600. Because as
Yeah, me
mentioned, the guided camera Nick is using also gets 15 to 25. But this is stuck at 5 frames per second or less.
Yeah, who knows? So he's using direct show, I think.
We're using that as
Yeah.
well. Yeah.
Yeah, so we'll see if there's other solutions or whether he gets stuck when we go to the 600. It
Yep.
might be something completely different about it that prevents it from working well. Anything else?
Just a comment about frame rate. When I was using the 290 camera, the ZWO 290 with what's the other software? I forgot the name of it already.
Fire capture?
Yeah,
or-
fire capture. It pulled down those frames just really, really fast. You could go with a very short exposure and get hundreds of frames per second. It's just like, the nominal performance is supposed to be from the camera. But with Dan's ZWO cam software on Firo, it was considerably slower. And Dan looked into that and he said there was some latency there because of the way the FITS files were required to be constructed. At least that was my takeaway from it. It took the I don't know whether it was calculation of the parameters that were, a lot of data in the FITS file and the FITS header, or whether it was something else. But it seems to me that maybe fire capture doesn't do that stuff in order to speed up the frame rate. If there really is latency in either writing the FITS header or in calculating the data for it, maybe that's an area where it could be cleaned up, because we sure don't need all the data in every file. Could put it all in one and then not put it in the rest maybe. But maybe there's an angle there that might be a way to speed up the frame rate.
Did he
Yeah,
write anything about that? It'd be great if you could forward that, because we've been thinking about that as well, but we don't know yet.
I don't really have any information other than conversations,
Okay.
and I don't know how fire capture does it, but I'm sure that the author of that software has spent a lot of time trying to get the frame rate up as fast as he can. So he might have found ways to do it.
It's a minimal FITS header, contains
Yeah, it
almost
really
nothing,
is. Hardly anything in there.
like 10 or 12 lines.
Yeah, exactly. I've used it before, a very short FITS header. Yeah.
Yeah, but that still takes 1024 blocks of data. That's just the way the headers are written, so.
Yeah.
Oh, also, Leon, any chance you could run some tests, saving it as a different file format? Another compressed type file format, see if there's a result different, because you can always convert them to fit and, and back process all the fit information you want in it.
Yeah, I think so. Let me check. Yeah, here we go. Yeah, it can save in the PixInsight format and TIFF as well. We could try that, yeah. That'll be a great test.
Yeah,
Actually, I'll do that right afterwards.
For what it's worth, we're getting at Barrow, it looks like we'll have our replacement for the focuser in place in March. And then we'll be able to go to Nina and we'll have a ZWO, the 1600, that would be available as well that way as another camera solution.
It'd be nice if it worked with, if we could make it work with all CMOS cameras, because they all have their own advantages and disadvantages. So,
Yeah.
I mean, the ZWO is about $1,000 cheaper. That's not to be sneezed at.
Yeah, but the buffer on the ZWO isn't as large. We're hoping to use that. Since the QHY 600 has a 2 GB buffer, we could save minutes of speckle images in there if we wanted to.
And maybe that's the way to go. Huh? You save the entire speckle run, you download it later.
Yeah, sure. Download it asynchronously then, yeah.
Yeah, asynchronously. Then who would care?
Yeah.
That might help with full frame frame rate also, if you need to take more than one image at a time with full frame.
Yeah, that's also something we did 2 days ago, turning the, well, it's a DDR3 memory buffer on. And so far the frame rate has doubled from that, but that's just casually using it. So what it's doing right now, it's the camera itself is determining what images it puts in the buffer. Then it sends it to the computer's random access memory, so RAM. And then after everything has been taken, it gets loaded out from the computer's memory onto the SSD. But the goal would be to save everything in the camera's memory, and only after the images are taken, then load it onto the SSD. So completely skip the computer's memory while it's imaging. And we don't know how to do that yet, but that's like, doing that is probably going to be the step from having 15 frames a second or 20 frames per second to 50. But since we don't really need more than 10 frames a second with most speckle exposure times anyways, that's like a longer process step.
Yeah, that's correct. We really don't need to go all the way to perfection here. I think, if you can get 5 frames per second with 50 millisecond exposures, that's still a lot of overhead, but it's really perfectly good enough for our purposes. So, you have to ask yourself where to stop. And if you get 5 frames per second, I think you can quit.
Yeah, well, we do get 5 frames a second now. It's just saving is the problem. But I'm going to try Tom's suggestion right after.
Are those downloading also as 32-bit images or 16-bit, or how are they coming down?
16. Yeah, 16.
Can you adjust that?
Yep.
So you could take it down, like say to 12-bit.
Yeah, we can, as far as we want. Yeah.
Dave, would that affect Speckle's ability to work in the toolkit?
You mean having what, Tom?
Having 12-bit images instead of 16?
No, as long as I can correctly interpret the arithmetic, the bits.
That could be in the header, so it's not a problem.
Right.
How many bits are in the ADC in that chip? Are there 16? It isn't 16, is it?
The 600 has 16-bit.
It has 14 point something, and then they use some trick. I forgot what that was.
Okay.
It has 14.9, but yeah, basically 16.
Yeah, so 12 is generally enough. I mean,
Yeah.
you're not going to lose anything in speckle because you're averaging, hundreds or thousands of exposures together in the end. So it doesn't make very much difference at all.
Yeah.
How short
fact, it
exposure
doesn't-
time can it be for on the QHY? Dave was saying 50 milliseconds, but we often are running below that. Can you make them shorter than that?
You can go into microsecond range,
Oh,
a few
okay. All right.
microseconds.
All right. So it's just a matter of what the throughput is for the imaging run. Okay. Okay.
Okay, anything else?
Okay.
So we'll continue working on that. It sounds like we're getting close to a solution. Leon and Nick are probably, they might even be there if they can figure out this weird conversion problem, whatever it is. Okay, so I had a couple of things. I'm having a star party on the 1st, 2nd, and 3rd of April. 1st, 2nd, 3rd, and 4th, which is a little bit early, but it's that's the weekend after the Mount Wilson weekend. I know that's kind of a strange thing to do, but that's okay. So Russ and Dan and I have already arranged this. I'm interested in gold prospecting, so we'll do some of that, of course. And I'd like to know if anybody wants to go.
This is your place in the desert, right?
It's at my place in the desert, so there's limited seating is available here. So the cabin is kind of taken with Russ, Dan, and I, but there's an observatory and a bunkhouse. So the bunkhouse has three spots, 3 or 4 spots to sleep, and the observatory 1 or 2, depending on how friendly you are with your neighbor.
Room for a motorhome?
And there's lots of room for, yeah, it's a 40-acre lot. So like you can park it kind of anywhere. You park your motorhome. If there's more than 5 of us, then I need a pickup truck that's already pre-scratched up because there's lots of interesting things in the desert that tends to scratch your truck, but or we can chip in for a $200 buffing, whatever you call it, where you know the guy buffs out your car after you've scratched it up.
And you would also need a really wild driver to keep up with Dave.
Well, I can slow down a bit, you know. And this doesn't have to be a real, you know, kind of dangerous adventure. This can be anyway, so think about it. But so the first Friday is the 1st, I think. So it's Friday night, Saturday night, Sunday night, and I'm driving back Monday the 4th. And you can get picked up in Las Vegas if you want, because Dan and Russ will be in Las Vegas on Friday and they'll return Monday. So there's a lot of ways of getting, and I'll be driving out Friday from LA and so forth. So.
Yeah, I might like to go again, but depending on how wiped out I am from Mount Wilson.
Well, yeah, me too. I'm expecting to be recovering for the next 3 days after that. So, okay. And the last thing is Leon had some questions about CCD, or I'm going to call it now CMOS SNR spreadsheet. And we plan to talk after this, but you know, maybe there's no reason to switch to a different Zoom room. Maybe we can just do it here, and the people that aren't interested can just drop off, you know. Okay.
That sounds good to me.
All right. So Rowville on the 1st, be a star party without a telescope. It's a naked eye star party. Okay. I have a little 6-inch, huh?
I would love to, but I won't be able to I won't be able to get away during school, but I'm curious if you're going to talk about the spreadsheet. The thing I was going to ask about was, I was thinking about how you the spreadsheet, if I understand correctly, is geared toward choosing an aperture size. Is that correct?
Well, the spreadsheet is just a general tool to model the process of obtaining images from stars and analyzing noise sources. So really, it's pretty general tool.
Yeah, I was just thinking of using it in a different project with like micro observatory images, which is going to make Leon shudder. But I was just wondering how applicable it would be, and I couldn't think of any reason it wouldn't apply. So maybe you have thoughts on that.
Yeah, well, we can talk about that in this next session that we're about.
Okay, I'm gonna have to also leave at 11:30, but I'll listen to the first 15 minutes eagerly. So please go on.
Okay, so everybody else feel free to drop off if they're not interested in the subject. And I'm going to let Leon ask questions. And the rest of you ask questions too. I mean, we can go over this as many times as we need to.
Great.
Hey, Dave, before that,
Yeah.
are you still looking for operators for the 24-inch or
Yeah,
where did that
of
go?
course, right. That's always that's an outstanding offer. You know, Leon and Sophie know how to operate the telescope. Before I can let you do that, we need a document about the proper way of turning on and turning off the scope. Really the single difficulty that kind of remains is turning off the camera, cooling. And you don't even need to cool the camera if you don't want to. It doesn't make really any difference to speckle. It does make a difference if you, well, yeah, there's certain things that it might help with in data reduction, but they're minor. So even if you don't turn on the cooling, not a big deal. But if you don't turn it off, then it's a big deal. And you have to turn it on and off with a 5-minute, warm up and cool down, or 3-minute warm up and cool down time. And really, as long as those things are practiced correctly, then I don't think there's any reason why, you can't be an operator with a night or two of, or an hour or two even of training. You should be able to run the telescope.
Okay. Well, let me know.
Yeah, well, it's really, I think you should schedule that with.
Well, what I'd like to do is sit in on some of the sessions that Sophie is having and really kind of watch how she does it. And that'll be a big help.
That's the right way to learn. Yeah, just watch for a while and then try taking over the operation. Sure. Eventually, there's not going to be an operator really needed, except to start the thing up at, at dusk and turn it off at dawn. The software, Nina will turn on and off the telescope really in a graceful way anyway.
Yeah.
Okay. I was curious about that exoplanet run last week, I guess it was. Was there data acquired, or how did it turn out? I don't remember who was observing.
Are you talking about the HIP 65 AB? That's not till next week, if that's what you.
Oh, okay.
Yeah. Do you want to see their call for observations? I think it's lovely. I will link it in the chat.
Yeah, great.
Now, I already read through it from the Exoplanet Watch Slack. That was very nice.
Okay, so Leon, why don't you begin?
Yeah, I can share the spreadsheet. Where is it? One moment. Oh, and by the way, on the side, if you can say on the side, the time lapse we did of James Webb earlier last month with the CDK24, I put that on YouTube, and that's really gotten a lot of views. Like in the last days, it sort of exploded. That's on track to getting 100,000 views, I bet, in a few weeks.
Oh, wow, that's great.
Yeah.
So they just started to take some star images and they're collimating the individual pieces, mirror sections, and it's all very exciting. Right?
Yeah, I saw that. And the selfie, the mirror selfie.
Mm-hmm.
There we go. All right, this is a slightly modified version. We already did some writing here months ago. So I guess the question is the calculations you do here for scintillation, all this, and sky glow, sky glow noise. I understand what the sky glow noise is, or what these values mean, but I don't understand how you get to these scintillation values. Which,
Okay.
and this is key for interpreting, because here you can see with this, I think this is, no, this is my old telescope, I think, like my SCT, it makes up 62% of the photometric noise. So understanding how you actually get to this value is key.
Okay, so the reference for scintillation is what's his name? Russ Andrew Young, I think, did the original calculation, and I used his calculation. He sets a scintillation, I think it's Andrew Young, yeah. And it's given up here. I don't have a pointer, but the last in the references, the last entry in references, line 10. So it's Astrophysical Journal, August 1967. And so what that is actually telling us is, you know, the atmosphere is correctly modeled correctly. It's a very complicated thing, but what we assume is that the turbulence is in a power spectrum that's called the Kolmogorov spectrum. Famous Russian mathematician worked it out.
I'm gonna go wrong.
No, it's K with a K, Kolmogorov, Kolmogorov, with an F on the end, I think.
Oh, an F or a V?
V, yeah, or a V or an F. Yeah, and so that's a power spectrum for turbulence, and he worked it actually out mathematically. The way that it works is quite interesting. I won't delve into it right now, but Andrew Young took that turbulence model and asked, well, what would the diffraction be like? Refraction. What would the refraction be like if the atmosphere were purely Kolmogorov in nature? Okay, and he was then able to calculate the amount of scintillation that the starlight experiences in and out of the aperture. So scintillation is actually, the light is refracted, and some of it's refracted outside of the aperture of the telescope in time, of course, and that varies with time. So it varies with the length of exposure and with the aperture diameter and so forth. And if you click on that that expression, we can go through it in detail. So F14, we start with F14, which is the obstruction diameter, right? And let's see.
F14 is the signal.
The aperture diameter, right?
No, the signal.
Oh, sorry. I'm sorry. Yeah, I'm misinterpreting. Good. So it's the total signal, which makes sense. It's the total number of photons. Right?
Yeah.
So look, this column of stuff here. This is the scintillation in basically photoelectrons over your exposure time. So it's the random component due to atmospheric refraction over the time of the exposure.
Right. So all this is just this is calculating the scintillation, and this is multiplying it by the signal I actually get, i.e., how much
Correct. Right.
Okay.
So
So
now
I'll
we
just
start with.
take that out. Just
Okay.
so this would be a coefficient, a scintillation.
So
Or
I
what-
think B28 is actually Andrew Young's scintillation coefficient, which is for a kind of an average atmosphere. So again, it's going to depend crucially on the type of atmosphere you're dealing with. If it has a high spread of temperatures or a lower spread of temperatures, if you're higher up in elevation or lower, and what wavelength you're talking about, all of that is embodied in his scintillation coefficient. So this is a highly kind of empirical result. After all of his calculation, you end up with something that's fairly complicated, depending on a number of different things. So in his paper, he says he found that the average scintillation coefficient was about 0.05 or 5%. And I just took that. So I'm sorry to say that this isn't very precise in any sense of the word. It's kind of like the extinction problem. The extinction can vary over an order of magnitude nearly, depending on if you're in the Sierra Nevada in the summer and there's a bunch of fires, then the extinction can be really weird, and you have to be careful if you do photometry.
So if
So
I
really,
would look,
if you were trying to get an accurate number for it, you would pretty much have to be an atmospheric physicist. I mean, it's not the variability is pretty complex, isn't it, Dave?
Yeah, it is. And that's why, we have to wave our hands a little bit, our arms in the air about this, but it can often be the dominant effect when you're doing photometry. So you have to take it into account, unfortunately, and it varies from night to night. But I found that this is probably his guess was probably a pretty good guess. Around 0.05 gives you generally a good answer.
do you know the uncertainty on that coefficient? So let's say it's on average 0.05, but I now want to get a minimum SNR. So what's the worst it typically is?
Yeah, that I'm going to have to let you go research. If I
Okay.
gave you any answer, I would be misinforming you. I think you got to go take a look yourself. People do experiments to find out that number, and a lot of work's been done. So yeah, just go look for it yourself now that you know what it kind of means. But you can look at the form of the equation. There's a 2/3 power, there's a -2/3 power in the aperture, which sounds weird, but that's actually kind of the circumference. In a way, it's modeling the motion of the light in and out of the circumference of the mirror, which is where all of the scintillation happens. It happens right at the edge of the mirror. So, and then there's a factor of, trying to remember, there's a square root of, what do we got there?
Oh, 1/2.
B21. it goes like the, yeah, it goes like the square root, 1 over the square root of the exposure time. And that's the random noise thing that we always talk about, right? Noise is always going like the square root of time.
Right, and then
Okay.
multiplied by the air mass, because that's very important.
Yeah, and then the air mass is important and so forth, right? And then we have this exponent, right? We have this exponent of the elevation, which is also, it's an air mass issue.
Just,
Okay,
yep, just for trying out, I'm going to. Okay, hardly makes a difference. Yeah,
yeah.
okay. Yeah, well, I'm close to sea level here. But a question, you mentioned the scintillation happens right at the mirror. I thought it's an atmospheric effect.
It is, but the photons going in and out of the aperture of the telescope happens at the edge of the mirror. Right?
Okay.
Yeah. So if you read his paper, it would help a lot.
Dave, can you think of it as sort of a cylinder of light coming into the aperture of the mirror? And the atmosphere is wiggling that cylinder back and forth so that the edges miss a little bit.
Yeah, you can think
sometimes.
of it like, you can kind of think of it like that, but I think it's better to think of it as the light hitting the mirror. If there were no atmosphere, those photons that came down through the atmosphere or the lack of atmosphere, that cylinder, hit the mirror and end up at the sensor. However, what happens is that the light near the edge is being constantly refracted in and out of that in a random way by the turbulence in the atmosphere. And that's what he modeled. And that modeling is interesting to read the paper, how it's done. But yeah, it's basically the cylinder of light coming down to the mirror. It's that cylinder that's near the edge of the mirror that makes all the difference, because you don't care if the light got refracted to a different part of the mirror, then you wouldn't change the number of photons hitting the sensor. So all of the action happens right at the edge of the mirror.
It seems like there's an effective aperture that might be plus and minus, because a bigger aperture would catch a bigger cylinder, and yet maybe that makes it more prone to small variations around the edge because there's a much bigger edge also.
Yeah, so this is a fractional effect. So you're
Right.
looking at the fraction out of the total that, misses the aperture, or that goes the other way. So it's a random effect. You can have more light or less light, and that's scintillation. When you look at a star with your naked eye, the same thing is happening. Light from that star is being refracted through the atmosphere, and it can either miss your pupil or not, and it's a fractional effect. So the bigger the mirror, the less scintillation you have, but it only helps as the minus 2/3 power, which is kind of odd. But if you work through his discussion, then you can see why.
The bigger the mirror, the less scintillation. Is that a linear thing compared to the mirror area, or does that?
No, it's the aperture to the minus 2/3 power.
That's to the minus 2/3. Okay.
Yeah.
Okay. I don't know why minus 2/3, but I'll have to read that up then.
Yeah. Mhm.
Right. And next thing I wanted to ask is, if I know this is not the sensor noise we're looking at here now, but this is the photometric noise. But if I would be observing an exoplanet or doing photometry on a variable star, I would typically, if it's a let's say a 12 magnitude target, I would take a 30-second exposure. But according to this, if I decrease the exposure time to 3 seconds, so looking at the SNR here, it would be for 130-second exposure, it would be 121 or 122. But if I would decrease that to 3 seconds, which is essentially introducing the bias noise every time, even though it's very low here, and then do 10 of those, then I get a higher total SNR than if I would have just taken one. So you get this by multiplying by the square root of the number of exposures, and you've explained that before. But intuitively, it doesn't really make sense to me, because you are averaging out the noise, but with every new exposure you take, aren't you introducing more noise from the camera, bias noise? Or is this only something you can do now that CMOS cameras have such low noise?
Okay, so there seems to be several questions wrapped up in that. So let's go through what happens when we average a bunch of noisy images, right? And let's consider averaging the noise of just the star itself. So if I take the star and I take it again and I average, so I take an image of the star and I count the number of photoelectrons, pure, just counting. And I get 1,000 photoelectrons. However, there's a noise in that of plus or minus 1 sigma noise of, say, 100 photoelectrons. So my signal to noise would be 10, right?
Yep.
Now, I take, let's say I take 100 of those measurements. So now the number of the total average number of photoelectrons is now 100,000, right? I took 100 exposures. Each exposure
100,000 or 10,000? Well, how many do you?
I said 100 exposures.
Oh,
So I took 100 exposures, right?
Yeah.
And of a star that gave me an average count of 1,000 photoelectrons.
Yeah, that would be 100,000 then, yeah.
Right. So it grew, of course, by a factor of 100. But the random noise, because it grows as a square root, only grew by a factor of 10. So my signal to noise ratio, so instead of having 1,000 plus or minus 100, I now have 100,000 plus or minus 1,000. So my signal to noise ratio is now 100 instead of 10. And that's because I took 100 exposures instead of 1. And the SNR grows as the square root of the number of exposures. Okay. Now, is that part clear?
Yes.
Okay.
But aren't you, the only, that makes sense to me. The explanation is logical, but by taking a new exposure, you're adding even more noise into that calculation.
You are, but that noise grows as the square root of the number of
And you're adding signal linearly and not as the square root.
Correct.
All right. Yeah.
So signal adds linearly, of course. The average just, let's not even call it an average. We're just summing 1,000, the average, 1,000 each time on the average to get 100,000. The noise, on the other hand, is because it's random in nature. It's the random walk problem. Every time you flip a coin, and let's say the coin has no bias, then you get an average of 0 if you take heads as being +1 and tails as being -1. Every time you flip it, you get 0 on the average. But the standard deviation of the count is going like the square root of the number of coin flips. So it's growing as the square root of the number of flips. So if I flip a coin 100 times, I'm going to get 0 plus or minus 10. And if I flip it 1,000 times, I'm going to get 0 plus or minus 30. And that's was proven, I think, by Gauss. He was a brilliant guy. Anyway, it was proven a long time ago mathematically that that's what happens with when you select random numbers. And it's a very beautiful theorem, and you should study it because it's quite important. So again, if you take 100 exposures, the SNR will go up by a factor of 10, not 100, but by a factor of 10.
Right. So the only reason not to take more exposures over a 30-second period is the download time from the camera, which isn't a factor anymore with modern cameras.
Right. So, and the read noise. I mean, every time you read the CCD or the CMOS camera, you inject a fixed amount of noise called the read noise. So it's better to not take really short exposures where the read noise is becoming a large fraction of the total noise. Right?
All right, so there's a sweet spot in there you can calculate.
There's a sweet spot you can calculate. Yeah.
Right, good. What else? Was the you once going over this spreadsheet the first time we looked at this, you mentioned to just leave the shot
Noise penalty, right? So in
why
the
at
days,
0?
Well, that's for EMCCD cameras, and EMCCDs. I don't know if you know how they operated, but
Yeah,
what happened? You got one photon produces a whole bunch of photons, right? So, in the plate that's used to amplify the optical signal, a single photon will create many, many photons, and it will swamp the read noise of the camera. So that was popular when we had noisy cameras, when the read noise was 10 or 15 or even 20 electrons per read. That's very noisy. So it was better to amplify the signal optically in this, scintillation plate, as they were called, or photon multiplying.
Where would that be located?
So
Like
yeah,
in the pixel.
So these photon multiplying devices are quite interesting. What you do is you create little tiny channels. So imagine a plate that's made up of a bunch of fiber optical fibers that have been fused together. That was one way of making it. And so there could be many thousands of optical fibers, or even hundreds of thousands of these tiny little channels. They're called microchannel plates. And you put a high you dope the material in there, and you put a very large electrical field across the microchannel plate. And what that does is, as soon as a photon dislodges an electron, that electron is accelerated and crashes into more of the lattice, which produces a shower of more photons, and that process gets repeated. So one photon can produce, thousands of photons coming out the other end of the microchannel plate. And you put that at a convenient place where you can focus it on the back end of the microchannel plate is then focused onto the sensor, the CCD.
So would this be included in the camera, or is this something you'd
This
screw
was
on the front?
included in the camera. So
Yeah, so fairly close to the sensor.
right. So now you focus the light not onto the camera sensor, but onto the top of the
Right.
microchannel plate. And all this stuff happens in a region of a millimeter or so. And then the camera sensor itself is focused on the back of the micro channel plate. So you get the idea. And it worked really well. And then they then found a way to actually incorporate the microchannel plate on top of the sensor itself, so there wasn't the secondary optics that you need to refocus the light and all that. So it became a very popular scientific instrument for about a decade. But with CMOS cameras, they're basically disappearing. Nobody uses them anymore because CMOS cameras have a very low read noise and very good quantum efficiency.
So it's just the production cost of adding an entire plate.
Yeah, they're very expensive
Yeah,
things.
I can imagine.
Yeah.
Yeah. So what? And back then, so it would be the micro channel plate, and then below that, you'd still have micro lenses on the individual pixels.
They did for a while, and then they stopped doing that, and they just put the microchannel plate directly on top of the sensor itself. Okay, so the shot noise penalty has to do with the way those microchannel plates work. And the way they work is if you use an EMCCD, you set the read noise to 0, but you set the shot noise penalty to a factor of 2 higher. So you have to add a factor of 2 to the photon shot noise, and it turns out that that's exact for a physical reason that
Wait, so I'd set the read noise to 0.
If you use an EMCCD camera.
Yeah, of course.
Okay.
And then I need to multiply this by 2, but this is in decibels.
No. So
Oh.
if you read line 6, it tells you how to deal with an EMCCD camera.
All right.
So 3 dB is a factor of 2 in intensity. Otherwise, you set it to 0 if you're not using an EMCCD.
Right. Okay.
Okay?
Right. Yeah, I was just
So
wondering what decibel value the factor of 2 would be. 3. Okay.
Yeah, 3 dB is a factor of 2. Okay.
So the shot noise penalty arises from the random generation, the random generation in the multiplication of the microchannel plate, not the shot noise of the photons.
Right.
Right.
It's quite a strange thing to me. And I honestly would have to go back and look at the physical explanation for it.
Yeah.
I
It's
don't
not
remember.
it's not the random arrival rate of the photons themselves. It occurs in the microchannel plate.
Oh, yeah. It's
Okay.
like, yeah. Okay. So there's quite a bit to that too, but there's plenty of literature about it. If you look at if you just Google the shot noise penalty for EMCCDs, you'll find all sorts of information about it if you want to know.
Okay.
And why is it called a penalty if you're trying to get rid of read noise?
Well, because the read noise goes to 0, but you've increased the effective photon shot noise by a factor of 2.
Okay.
So it's a penalty. If the photon shot noise is itself a very low part of the total noise, then EMCCDs work really well because they zero out the read noise. But in the example you have in front of us, the photon shot noise is actually much higher than the read noise in terms of total photoelectrons. So in fact, using an EMCCD would make the noise a little bit worse, not much, but a little bit, than the CMOS camera. So, as soon as we had large format CMOS cameras, EMCCs, went extinct.
I'm not sure if this question makes sense. How would I incorporate the camera's bit rate into here? Because obviously it's just the matter of how I divide up the full well signal. However, doesn't having a lower bit rate and thereby summing a larger range of ADU values, or let's say, let's stay at a 1-to-1 conversion, let's say photoelectrons. So I'm summing more, giving me less total information. Doesn't that introduce a form of noise?
Yeah, so that's called digitization noise, if I understand your question correctly.
Yeah, it sounds, yeah, sounds right.
So let's say I have a perfect sine wave and I digitize it, right? And I have, say, 2 to the n digitization levels between, peak to peak or
Yep.
peak to valley. So it turns out that there's an expression for digitization noise for that sine wave that goes like it's 6 bits. It's 6 dB per bit of information. So if I had a 10-bit A to D, then I would have a dynamic range of 60 dB. And the amount of noise that I'm adding is quantified as the digitization level divided by 12. The RMS noise that I add to a sine wave that I've digitized that has a peak-to-peak number of bits of n, okay, is 1/12n RMS.
I over 12.
1/12n, and that's the RMS noise that I've added to it. And
but why over 12?
well, that's when you do the calculation. Okay, so take a sine wave, or just take a linear ramp, right? And my A to D converter is actually turning that into a step.
Yeah, I mean, just for context, we actually I covered this topic in university briefly like a month ago, but we never went into the noise, just the fundamental concept. So I know what you're doing with the sine wave, converting it into steps.
Right.
We went from analog to digital and digital to analog. Just only the principle, not the side effects like noise.
Right.
So I have some rough understanding of that, just not how you.
So the way we write a system model when you have an A to D converter or a D to A converter is you put a little noise source in front of it or back of it, depending on which side's the analog side, right? So, and that noise source has a RMS power of, well, let's talk about amplitude first. It has an RMS amplitude of 1/√12n. So it has a power of 1/12n because you square it to get a power.
Wait, you take it and take it to the power of 1/12n?
No, you need to give me the blackboard for a second.
I think you can draw on my screen. Should be.
Can I draw over here? I don't know. Can I?
There should be annotate or something.
View options, annotate. Okay, let's see if I can.
Right.
Yeah.
Let me just move this down here, and you can. Here, there's this white area here.
I got it. So when you take a sine wave and you digitize it, you get the steps. And now I'm going to flatten out the steps to show you what the noise looks like. So the noise is going to look like this, right? It'll be some randomish looking thing that has about 1 bit of, this will be roughly 1 bit of noise, right? Because if I take my pure sine wave and I look at this region right in here or any other region, but It gets complicated because it gets flat here. So there's a lot of you have to do the integral correctly and so forth. A little bit complicated, but not too bad. If I look in here though, I see these steps, right? So the output is the sum of the correct wave plus these plus and minus little steps. So about 0, here's 0 up here. And
Wait, plus
I
and
call
minus doesn't that perfectly average out to 0 if you take the steps overcorrect and undercorrect?
that's
Or-
right. So they're a little bit too high here and they're a little bit too low here. They all kind of average to 0. So that's the noise source that I put in my system model to model. So if I have a D to A converter,
Yeah.
right? D to A converter. So I would add a noise source here. So I'm adding noise to this, and that's my output. It doesn't look like that, but you get the idea. I'm effectively adding a noise source to a otherwise perfect signal. I consider this perfect. So if this is n bits wide here, I first consider it to be infinitely wide, in other words, infinite resolution. And then I add a noise source to represent the fact that it's not infinitely, doesn't have infinitely high resolution. And that noise source is this thing. It's random. So as a system engineer, I don't care about the details. I only care about how much average noise it adds to digitize my signal. And so what I get is this noise source, which I should have written as a small n.
I can't see your cursor, by the way.
You cannot?
I can only see what you're drawing, but not the cursor.
Oh, I'm not, you're okay. So.
Well, you can share your screen if you, but then this is gone.
No, this will work.
Okay.
The random noise is characterized in this is an amplitude of noise. And if I recall correctly, the amplitude is 1 over not the number of bits, but the total resolution of the D to A converter. It's 1 over the square root of 12 times, I'll call it 2 to the n, where n is the number of bits.
Okay.
I believe that's the correct expression, but I have to go
Yeah,
back.
I'm going to have to look that up, especially the factor 12. I don't know where that comes from.
Yeah. Now, why is it
I think
a factor?
the factor of 12 is just the standard deviation of a square wave.
Of a triangle wave.
Of the width of a square wave, yeah. Of a triangle or a square?
Yeah, I think this turns into a triangle wave. If you look at this region down here, you'll see it's the sum of the ideal sine wave plus something that looks triangular in nature or sawtooth in nature. And it depends on, you have to normalize this correctly. There's a lot of mathematics involved in this that you don't really ever have to know. You just have to know what it actually is, what the answer is. And systems engineers who do electronics, they know this like the back of their hand. It's an expression that looks like this, and then you go look up the details knowing that you have to add noise to this, from a system engineering point of view, just go look it up, Leon, okay? And you'll see the explanation for it if you're interested in, but it's a fixed amount of injected noise because of digitization. Okay. A very important, it's extremely important in electronics when we calculate the noise of a transmission system. I mean, there's lots of A to Ds and D to A's involved in that. not only in the receiver itself, but in the phase lock loops that create the frequencies that are mixed with stuff and so on and so forth. There's a lot to this, but just know at this point in time that whenever you digitize something, you pick up some noise.
Right.
Right.
So I understand the principle, but this is a small factor now, right?
It's a small factor for us generally.
What to get to calculate the actual digitization noise
Mhm.
with a signal, would I multiply the signal by this factor or?
Right. There's a lot. Yeah, that's a really interesting loaded question. So let's take a single pixel. Of
Sorry, I'll just
information.
move there.
That's okay. We'll take a single pixel and we'll say that there's a certain number of photoelectrons that we received. So that's embodied in the photon shot noise, right? We've talked about that.
Yep.
That a certain number of photons arrived here and we multiply that by the QE and we get the total number of photoelectrons. That's basically that's the primary digitization in a CMOS camera, is the fact that photons come in individual packets. Now, the A to D converter that I then use to take that information in photoelectrons and turn it into digits, you know, this is a 12 or a 16. This is, for us, you know, some few number of photoelectrons. It might be 1,000 photoelectrons or something in a pixel, maybe less, right? Full well being what, you know, 40,000, 20 to 40,000 or something. So then I digitize it into n bits. And so I have to add here my digitization noise source, n, we'll call that little n, naught, as it's known. And so it's almost always true that the photon shot noise that occurred here dominates this noise, because this, you know, this is pretty small. It's 1/12n in intensity. And so this noise here is a very small component, generally speaking, of this. And I've ignored it over here. It's not in that calculation at all. And so to do that right, you'd have to add yet another noise source in the system in front of your A to D converter. I know you can't see my cursor, but okay.
Yeah,
so,
if you click on something, it makes a small dot and then I can see it.
yeah, so you get the idea.
Yeah.
But
this noise is unremarkably insignificant.
Is almost always insignificant unless the number of photons you're receiving per pixel is very large. Then it might be a factor, but it's generally just not a factor.
And the can you see my mouse, by the way?
Yeah, I can see.
Yeah. The deviation in the AD conversion from pixel to pixel, since in a CMOS camera I have an AD converter on every single pixel.
Mm-hmm.
That deviation is the flat fielding error, like of the pixels, or is that the correct term? The pixels?
No.
What term is that?
Flat fielding error has.
I know flat fielding error is from the optics, but the pixels, they also deviate slightly, right? And you calculate, you can remove that source of noise with bias frames, right?
Okay, so yeah, so flat fielding error actually has to do with the difference in gain pixel to pixel.
The difference in gain.
Yeah. Okay, so let's suppose that I assume I've got a, let me see how I can describe this. I've got a, a 3x3 box of pixels maybe is a good way to start. Let's see if this works. If this idea works. And now I uniformly illuminate that box, right? With photons. And I get a certain number of photons in each one of those boxes. That's different because there's a certain probability that I'll convert, even though I've illuminated it uniformly, I get photon shot noise actually changes the number of received electrons in each box. So that factor is already contained up here in the photon shot noise. However, each one of these pixels can have a different amount of gain, right? So G, we'll say G, it has gain, this one has gain G0, this one has gain G1 and so forth. So
Yep.
up to G8. So if this comprises my star, then when I measure the star, I have to add the photoelectrons that were generated in each one of these 9 boxes. So I have to multiply the number of photons received. We'll call that little n. And we have to multiply that by the gain of that pixel. And I have to sum that over all of the pixels in my star image. And if I did that without knowing this G sub n, I'd be in trouble, right? Because I wouldn't actually know the individual gain of the pixels in my sensor. So I first measure that, and I call that the flat field, but then there's noise in that measurement because I can't measure the flat field perfectly. I can't measure these G sub n's perfectly because it's another quantum mechanics. It's basically limited again by randomness, by quantum mechanics. So what people say is I have to measure a certain number of photoelectrons per pixel to be able to determine what these gains are to sufficient accuracy to drive this flat fielding error down to something that, where's the flat fielding error? Flat fielding noise here, yeah. This guy. I want to drive it down so that it's a small percentage of the total error. And to do that, I have to measure the gain by collecting enough photoelectrons that randomness is reduced to some very small value. Like we love to, in the old days of CCD imaging, we love to drive that down to less than 1%. In order to do that, let's talk about how many photoelectrons I have to have per pixel to get my to get a calculated value of G below say 1%. Well, if I collected an average of 1,000 photoelectrons, then we know that the noise is going to be the square root of that. So 1,000 over 30, or 1 over that, 30 over 1,000 is, that's 3%, right? 30 over 1,000 is 3%. So I've got to do better than that. So if I do 10,000, then I'd have 100 here. The square root of 10,000 is 100. So that would drive it down to 1%. So I have to collect at least 10,000 photoelectrons per pixel to get it to a 1% value. And it's actually, you have to do better than that, it turns out, because you're actually looking at the gain distribution. So it's really the difference in gain between pixels in this array. And in the end, you end up needing around 100,000 photoelectrons to get down to a gain variation or gain measurement of like 0.5%. Something like that.
Yeah, but this gain variation is not static or constant, right?
It's
Un-
constant. And
It
we
is.
assume that
You
it's,
s-
well, we have to assume that it's constant. Otherwise you can't get anywhere. So, and it is more or less constant. It changes slowly with time in CCD sensors, like over a period of 3 months or 6 months, it'll change a bit. And you'll have new hot pixels and so forth that you, yeah, for CCDs. Now for CMOS, I have no idea. I haven't looked at what CMOS cameras do in terms of gain variation as a function of time.
I'd expected it to be higher, right? Because I have more AD converters.
I don't know. Or you could expect it to be lower because in CCD cameras, it's really due to defects caused by temperature cycling and cosmic rays cause lattice defects. So as soon as you have a lattice defect, a number of things change. One is that you start to leak out electrons faster, typically, because there's now often a path to the substrate where the electrons you've accumulated in the well are kind of slowly leaking out. So it's a complicated thing that depends on temperature and exposure time and, you know.
And why would CMOS be less affected by this?
Well, it may or may not be. I don't know.
Okay.
It's not necessarily true that CMOS is worse or better. I just don't know the answer.
Oh, it's something to measure, but I don't have
It's
a
something
CCD.
to measure or to go research. Yeah. A lot of this has already been done if you know where to look for it.
Yeah, I bet.
Anyway, so that's the nature of flat fielding errors is really this gain variation business that we're looking at here. So you get rid of
that's
that
a-
by taking. Mhm.
So that's a gain variation, and this N0 we've defined up here.
That's a digitization.
That's a digitization error.
And they're completely unrelated.
Yeah, because one is just the digitization, and after that you multiply where you have the gain variation.
Right.
Or, yeah, multiply.
Right. Yeah, more or less. Right. You got the idea. Right.
Good. Okay.
Yeah. So maybe you can erase all, or maybe I can erase.
I don't think I can. Yeah.
Can I erase it? Yeah. Okay.
Yeah, it's gone. About encircled energy, that's a smaller question.
Mhm.
That's just simplified terms. That's just how much of the point spread function of a star you capture with a certain aperture size.
Yeah, assuming some distribution of photons. So
Yeah.
so if I have a
Wait,
if I have a Gaussian distribution, which is what we assume, it's not true, but we often assume it to be true.
It's near Gaussian.
It's near Gaussian. It's actually probably more like a Moffett distribution, which has a different mathematical form, but you get quite similar answers depending on how you normalize things. But let's say my aperture only goes out to here, right? So that's the measurement aperture over which I'm measuring the intensity of the star by summing the photoelectrons. So I'm only measuring the photoelectrons within that region. Well, then I've forgotten these photoelectrons out here, and I've forgotten these out here, right?
Yep,
They're
right.
there,
So
but
I get that, but now the question is exactly what you just drew. At one point here, let's say the Moffett or the photoelectrons of a star will cross the noise floor of the camera. for
Mhm.
the background noise, let's say, because it's not just camera, you also have sky glow noise. Well, is it best to stop the aperture directly at the intersection of this noise floor and the curve? Or do I want to go, do I want to stay away from that or go slightly beyond?
Right. So that's a great question. It depends on what you're trying to measure. So if you're doing exoplanet photometry, you probably are trying to achieve the highest average signal to noise ratio, and you don't really care about the total number of photoelectrons that arrived. But if I'm doing absolute photometry on Vega or on a star, then I want to get all of the photons that I can, even though that would raise the noise floor a bit of my measurement. So if I start measuring these guys out here, these pixels, that suppose the noise floor is like here.
Right.
So if I measure all of these, then I'm actually raising the noise relative to the signal that I'm getting. And so I'm making the signal to noise ratio worse. But if I'm an absolute photometrist, I want to know what all of that energy had in it, all of that light. I want to know the intensity of that light. I don't want to throw it away because it's going to vary with atmospheric turbulence and right. So this stuff is going to be highly dependent on the condition of the atmosphere. And I might not want to throw that away if I'm a photometrist. However, if I'm an exoplanet researcher, I don't want that because I am raising the amount of noise relative to the signal I'm catching.
Right. Lowering the SNR.
Yeah. So
what about for astrometry? Let's say photocenter.
yeah, well, right. I don't know the answer to that. As you know, I think we've talked about that several times, and I'm still not sure what is the most appropriate thing to do. I think it's probably to throw that away, but you've got to do it consistently, right?
Right.
And that can be a bit of a difficulty because there's wavelength dependence and there's, hour to hour dependence and whatnot. It's a complicated question and I don't know the answer. But I'm sure you don't want to include a big, huge measurement aperture because that just drives the noise, way up. Yeah.
And I suppose you would, let's say you're doing exoplanet photometry, because this is what is being done. I suppose you would also want to vary the aperture then as, let's say you have more air mass.
Yeah.
Then the noise floor changes and you want to vary the aperture so you still hit that intersection point.
Right. So the photometrists actually do this variable integration, which is kind of clever. And you can watch the interaction of the signal with the noise, right? As you start the integration with a very small measurement aperture, there's not very much signal. And so the signal to noise ratio grows and grows as you open the measurement aperture. And then it starts to bottom out, and then actually the noise grows and there's a minimum. And Rick can probably tell us what that minimum is called. The photometrists have a name for all of that stuff.
I don't remember it. I don't remember.
Yeah. so
Richard Berry wrote up a nice little overview or simple explanation of that in his book, AIP for Windows, the book that accompanied this old software.
Yeah.
Back in the beginning of the CCD.
We could get Richard to give us a little bit of a lecture. So
yeah,
as a function of the measurement aperture, the SNR is going to increase for a while, and then it's going to start to decrease like probably the square root of the number of pixels involved or something like that.
I actually did that a little bit with Speckle in a way, and looked and did various apertures of the same speckle results. And you could see the trend. It was very, very subtle, but so I started at the peak and took the change in added signal versus radius. And it
Yeah.
became more sensitive, and you could see it declined as you went out further. You're gaining less and less light. And then it reached a minimum, and then it started to go up again. So it was kind of an illustration of that same effect, I think.
Yeah. And with speckle, we introduce a new thing because we're actually looking at the diffraction pattern of the telescope. So if we actually use speckle interferometry techniques to get rid of the atmospheric seeing distortion, then this whole game changes. And what
I
you
think
got,
I convinced myself that I could actually see the airy disk and the airy ring, the first ring, if the signal to noise was high enough.
oh yeah, it doesn't take much convincing. So, I mean, it's kind of obvious when you do it. You have a diffraction pattern in one dimension, which is much easier to draw, especially with a mouse. So you got a diffraction pattern that looks like that, right? Symmetrical on this side. And you can easily see that if you just do the integral that we've been talking about. You see it go through a minimum, and you see then more signal appearing as you intersect the first ring. And if you've got a large central obstruction, you can even see the second, diffraction ring.
Wait, why is the central obstruction related?
Yeah, that's a nice optical question. If you have no central obstruction, you get what's called the airy pattern or the airy function. And it has it's Bessel functions. The exact mathematical expression for it is a Bessel function. It looks like a Bessel function. And the peak, this peak is down a certain amount from this peak, and the area under the first ring is down from the area under the main airy disk, and so forth. It's all mathematically very nice. If you add a central obstruction to your aperture, then the amount of light decreases in the airy disk, and it increases in the rings. I should have used a different color, but I'm stupid. So, and you'll actually start to get, you can see more of these higher order diffraction rings. And in the extreme case where you just have a ring as the aperture, you have a very thin ring as the aperture. So make this ring go to be very thin, then you get a pattern that, looks like this. It has lots and lots of diffraction rings associated with it.
Right. So that, I think I've seen that, right? Rick, in your SAS presentation, you used a plane wave telescope, right?
No,
Because
I think it was based on the 22-inch, so it had aberrations mixed into the mess.
Yeah, because I could see like fourth order rings around it.
Mm-hmm.
What you showed. But does that mean if you do interferometry and reconstruct the image, does that mean you have to take the central obstruction of the telescope into account? Or
Right. So when you deconvolve with a reference star, that's already there. So
oh yeah, because it cancels out because the reference star has the exact same phenomenon.
right. So
Okay.
one of the values of the reference star is you get rid of most of it and you're left with only a residual. And that residual is very complicated. It has to do with noise also, and the inability to perfectly reconstruct any image, fortunately. Okay.
Okay.
So let's get rid of that.
What else? I think Sky Glow is already covered that. It was a surprising measurement last year to get the sky background, how much that deviates considering how full the moon is.
Yeah, sure.
But I've taken more measurements, and my sky background is 21.2, I think. 21.2, 21.3.
That's
Under
good.
under a new moon though. So
Yeah, in what band?
in V band.
That's quite good. So Palomar is 21.5 or so, as I recall. And so that's pretty good. 21 point anything, 21.0 would be considered a good rural sky background.
Is there any reason to, this is not that related to the spreadsheet, but let's say near infrared, going into the infrared cameras decrease in price significantly over the next 30 years, which they most likely will. Is there any reason to remain in the visual V band, or will everything move to gold-plated mirrors and near infrared? Because I've seen that PlaneWave already creates a telescope with gold-coated mirrors.
Yeah, we get a few requests every year for infrared telescopes for a number of reasons. One is the people that do infrared astronomy, photometry, using near infrared cameras that are J, H, and K band. So, J is around 1.2 microns, H is around 1.5, and K is 2.1 and longer, roughly
And
speaking.
I is just below J, right? That's like
And
900 to 1.1.
Yeah, then there's the Sloan bands, which go R, I, what are they? Y and Z, I think. For whatever reason, they named them that. And you can look at the Sloan bands that are Y. Y is around 900 and Z is longer than 950 or something like that.
So are those
they're
bands
all-
far better for photometry?
Okay, so we have to analyze all of the individual noise sources and the signal level to answer that question. When you're asking what the color of a star is, you usually do B minus R. And that's good enough for to get the general idea of what the temperature of the star surface is. And they often do it like Gaia, just with a B and an R filter. And they synthesize what we call Gaia G band from just adding the B and the R together, strangely enough. And that's good enough. Now, if you want to know details about the metallicity of a star, you've got to get more sophisticated, and the IR bands start to become important in the understanding of exactly where the star exists on the main sequence and the metal content, which is everything greater than helium. Everything above it's hydrogen, helium, and metals to the astronomers.
Yeah.
So it really depends totally on what information you want to know. If we're trying to do speckle, the atmosphere is quieter, a lot quieter in red and infrared than it is in B and G. Because of the atmosphere, the refraction of the atmosphere as a function of wavelength. So we often do speckle in R band because it's much less noisy than in G band or B. Even though we lose some information by not doing it in V. And Rick sometimes wants to know the V band information to be able to try to determine the color temperature of each star independently. There's a lot of physics to be done in the infrared. The infrared tells you much more interesting information about the amount of dust that intervenes between you and the star. So making infrared measurements can reveal other things about the path through which the light has traveled.
But pure infrared measurements, or comparing an infrared measurement to a V-band measurement
Almost always in comparison.
in
But,
comparison?
I think there's some people that do absolute photometry also in the infrared. And that's interesting too.
It seems more sensible to me intuitively, because even though, let's say, if you have a main sequence star which isn't that red, you will lose photons by cutting them off at, let's say you can't, gold doesn't reflect below 700 nanometers or something. So you lose all of that. But at the same time, if you're an earthbound telescope, most of the light pollution is, especially even moonlight, is going to be below 700 nanometers. And you also have to fight much less with the atmosphere. So even though you're throwing away a lot of starlight, you're also significantly reducing the noise sources. So it seems to me that in photometry, you would like infrared.
Well, okay. So first of all, gold is kind of minus blue in a spectrum sense. So gold contains wavelength, it reflects wavelengths down a bit below yellow.
Oh,
And that would be down to like 520 nanometers or something like that. So a gold mirror is fairly reflective above 520 or so. Nonetheless, you're throwing away a considerable amount of light. You can go find if you just Google on the reflectivity of gold coating, you'll find the spectral.
Yeah, I think it was at 700, it reaches near 100% reflectivity. And below that, I think that's the number I was thinking of.
Right. And then aluminum works pretty well out to, H band, but then it falls off considerably after about 1.5 microns, something like that. And that's why they like gold coating. Aluminum works well at J and H band, well enough that we don't actually get many requests for gold coatings. But the folks that want to do K band, H and K band, they like gold coatings because they're not interested at all in the light, visible light. They're doing infrared. Now, there's another whole customer base that we have at PlaneWave, which is the laser comm people and the satellite.
Yeah, the satellites. Yeah.
So it's better. It's much better if you're tracking satellites to use infrared because the atmosphere scatters much less light in the infrared, so you get much higher contrast, right? Especially near to the sun. They like to track satellites within a few degrees of the sun. So we do some special stuff even to the inside of the OTA to make it less bright, less reflective. And then we add filters and so forth. So the satellite people that track satellites, they like infrared, and the laser comm people, well, they're often doing laser comm at 1550 nanometers, the standard optical fiber band for long haul transmission. And it's 1550 nanometers for a very specific reason. That's where the dispersion actually goes to zero, believe it or not. An optical fiber made out of doped quartz, correctly doped quartz fiber, actually has no change in refractive index around 1550 nanometers. So the dispersion curve is flat at 1550, which is why we picked it for long haul optical fiber communication, like undersea, and for that reason, we have built up this whole technology based on 1550 nanometers, plus or minus, 50 nanometers or so. So the laser comm people that are trying to communicate with like satellites that are going to be around the moon or, in high, in geo or whatever, they're all using 1550 and they like gold coatings because for two reasons. One is they get higher reflectivity and they get lower unwanted radiation from visible, especially blue. So the fact that it's minus blue is a benefit, to gold coating.
I suppose you would also do that then if you're looking for near Earth objects in twilight near the sun.
Yep, exactly. Same idea. You want the atmosphere is very, very noisy in the blue. That's why it looks blue, right? So if you're doing stuff near the sun, you want to use infrared.
Right. I think that I've seen that before. A plane wave telescope, it has golden mirrors, is sealed. I think it was 0.7 meters.
Mhm.
And there was one picture with a delta rho on top. That was funny.
That one I haven't seen, but
The
right.
piggyback delta rho on the
Piggyback delta row, right?
yeah. Looked
So
so
there's folks
small.
that want to buy a bunch of delta rows and put them into weird arrays where they put 9 delta rows in a 3x3 array and they drive them all in the same mount and stuff like that. That's for doing asteroid detection
Yeah.
and also for other strange things that may or may not pan out, I mean, these are satellite people that are doing all kind of weird things with satellites. Yeah. So we'll see. And there's some folks that don't want any corrective. They want a very, very fast telescope and they don't want any lenses.
Because of wait, but don't those lenses pose a problem?
Yeah, well, I can't make a delta row like that, but I can make other types of Cassegrain telescopes like that. We don't want to.
Okay.
And if we use quartz lenses, they're pretty good all the way out to through K band, through KS, K short, as we call it. Yeah.
That's interesting. A 3x3 delta rho, right?
Yeah, 3x3 array of delta rows.
That's one hell of a amount.
And then I think I told you about the folks at the University of North Carolina. Instead of building something like the LSST to do wide field survey, what they want to do is they want to put, 1,000 telescopes.
Yeah, right. Yeah.
On a dome-like thing that rotates it correctly with respect to the sky. And they claim it's 100 times cheaper than the Vera Rubin concept and you get the same number of photons apparently. So, kind of
It
interesting.
amazes me that that's cheaper. That sounds so difficult to get funding for. You aren't buying. I want 100 telescopes with 100 detectors and filters.
Yeah, well, they're doing it. They're doing a pilot program of 40 of them. So they've ordered 40 from us. I think it's a 6x6 array with spare. So it's 36 telescopes.
Wait, what delta rows?
These are little 8-inch versions of
8-inch.
they're Delta Row 200. So they're little 8-inch versions. And we're building those right now. So it's 36 plus 4 or 6 spares. And we'll see if they get funding for the next phase. The next phase is to bump that up to, I think, 100 and some odd telescopes. It's like another factor of 4 more.
It sounds like a great telescope, an 8-inch delta row.
Yeah, it's a fun thing to
Yeah,
build.
it sounds really fun. With small
Yeah,
pixels, you still have the resolution.
And we're
I'll put that on the
building those
bucket
right
list.
now. Yeah.
Hmm.
So, there's a lot of interesting work to do in arrays of telescopes. And I don't remember if they wanted those gold plated or not. I don't think so. I think those are just V-band telescopes. Okay, well, I hope that helped, Leon. You have got a little bit of research to do. You're on your own. You got to look up scintillation and flat
Yeah,
fielding error
so
and stuff like
these
that.
two, going to read about microchannel plates, and I'm going to look through all of the references here.
Yeah, good. That's a great start.
Okay, my goal is that I can reconstruct every single equation out of here, write them
Yeah.
down on a piece of paper, and then calculate one single factor here, and then go to the spreadsheet, type in the same numbers, and have the same result.
Yeah.
Because that's really powerful, that I can then say, well, I can get anything I want. I can tell you the best aperture diameter or the best exposure time where you still hit a sweet spot of not going too far, where the bias noise starts to overshadow everything else, but you still get many exposures, so you can take the square root of images.
Yeah, that's an
There's lots
excellent
of
thing.
potential.
It's an excellent thing to do because CMOS cameras have really changed the nature of imaging. And we now have to become experts on the noise sources in CMOS cameras, and they're going to be different. And it's important to study that. And then you'll be able to tell people, the best set of exposures for an exoplanet transit might not be 30 seconds or a minute or 2 minutes at all. It might be 1 second exposures, stacked or, whatever. Yeah, I don't know the answer, but it's going to be different. Yeah.
A Calais project that Rick suggested, that's going to be interesting as well. Speckling that transit. I mean, it's a binary star, but still but I wonder what the effect on the one star is going to be.
Yeah, I mean, we don't know. So, there's lots of really neat stuff to do.
Yep.
And, I have to warn you that stuff like scintillation, it's not an atmospheric extinction and so forth. It's not an exact science, unfortunately. It varies over a range of values depending on the atmospheric conditions. And it's annoying, but that's just the way it is.
Turbulence is kind of like a last frontier of challenge for modeling.
Yeah. Yeah.
Maybe
never
there's a
solved.
way to approximate it. If I take the sky temperature and the wind at a certain altitude, I can get some better estimate.
Yeah, we'll start with Andrew Young's papers. He wrote several on this subject of atmospheric turbulence. And
wasn't Andrew Young the professor who did a lot of pioneering photometry at Cal State San Diego?
I don't remember where he was from now, Rick.
I kind of think he was at Cal State San Diego, but he was a sort of one of the foremost accurate photometrists. He always liked those narrow band filters. I forget what they were called, but the UBV. There's a different order of characters, and they were lowercase instead of uppercase.
Well, Leon's got the screen. Maybe he can Google it. Google Andrew Young for us right now.
That sounds like a very common name. Actually, no, this is
Andrew Young.
I vaguely recall a paper, a little talk he gave at some conference way back in the 80s, I suppose. And he said, basically oh yeah, there he is. Basically, you get better accurate photometry if you have narrower bands. Of course, you get less light, but the potential is there for greater accuracy too, because of
Mhm.
things I can't remember why.
Is this him?
That's him.
Yeah, that's him.
2007. In lots of infrared, yeah. Wow, he has done a lot.
Yeah, he was a relatively famous guy in the photometry business.
Let me see if I can just load all of these and then search for scintillation. Oh, that's a great title there. Are the clouds really of sulfuric acid? Looking at Venus. Oh, design of Cassegrain light shields.
Yeah, he's quite a guy, huh?
Yep.
There's a good
And
one.
it's
Yeah, 19, yeah.
huh.
Okay, so there are plenty of research for you to do if you want to know the subject more deeply. And it's a very deep subject. The problem with the atmosphere is that it's quite complicated.
Yeah,
So
I
just
just
have-
have to very sadly put it off because I'm going to have tons of exams coming up now. The
Mhm.
the last exam should actually be on the 24th of March.
The Mount Wilson day. huh?
Yeah,
The-
1 day
the
before.
One day before, right. Well, you'll have to get approval to take the exam early, a few days earlier, so that you can fly to Los Angeles.
Well, it should work. It's in the German morning.
And then you get on a plane.
Take the exam on the plane.
Right. Okay, well,
Oh yeah,
I have
if I
another
can-
call
if I
with,
can
I have
fly
a
out.
call with my colleagues at Planewave that I've been ignoring. So I got to get off to do that.
Yep.
Okay, guys, so we hanging up?
Yeah,
I'll,
very interesting side session. That's a
Yeah.
very
Yeah.
nice spreadsheet, Dave.
Yeah, I'm going to definitely look at the recording again on some point.
Yeah, I'm gonna get the
Right.
recording up. It's a good one.
Well, hopefully you'll, when you go through all of the equations, you'll be able to either validate them or find out where they're incorrect. Because having an accurate spreadsheet for signal and noise is very valuable.
Yep. I need to recreate that spreadsheet with a long fold out explanation next to each.
Well, it took me years to do it, so don't,
Yeah,
it's a
it's not a 1 week thing.
wasn't for me. Okay, guys, take
All right.
care.
See ya.
Thank you.
See you.
Thanks.
Bye.
Bye-bye.
Bye-bye.